In this mini lecture, we will be discussing the Doppler effect. Many of you have heard of the Doppler effect, and certainly even if you haven't heard of it, you have heard it. The Doppler effect is the change in wavelength of a wave due to motion between the source of the wave and the observer of the wave. And Doppler effect works for any kind of wave, be it a sound wave, a light wave, a wave on the ocean. They all can have this effect. So let's see how it works, and we'll use a little cartoon to do this. The cartoon that shows me on the left in my nightgown, and on the right we have an alarm clock called Clocky. If you've never heard of Clocky, I put the URL for a YouTube video showing how it works on this slide. Clocky is an alarm clock, and when it goes off, it beeps obnoxiously and its wheels spin in random directions, which causes Clocky to go off of your nightstand onto the floor and zoom around the room, which forces you to get out of bed in order to turn Clocky off. Let's use an example of Clocky for the Doppler effect. Suppose that Clocky beeps once every second, and suppose that the sound waves from Clocky's beeps move extraordinarily slow. So here you see a picture of me happy to be waking up. On the left, Clocky on the right, and Clocky beeped 1 second ago, and the green circle shows where that beep from Clocky is at this moment. Now let's suppose on this particular morning, Clocky is stopped and not moving. So a second later, the first beep will have moved further away from Clocky, and the second beep will have started and still be centered on Clocky. A second later, we will have a third beep. So again, beep 1 has now moved out even further. Beep 2 is moving outward from where it started. Beep 3 is moving outward from where it started. And even a second later, again, this continues. And what you see is that since Clocky is not moving, all the waves start at the same point. They all move outward from the point at which they start, and they are all equally spaced no matter what direction you are looking. So in a few more seconds, I will begin to hear the beeps from Clocky, and I will hear them come exactly 1 second apart. Now let's do this again, and let's suppose in the following morning, Clocky is moving toward me. So here we are, the first beep starts, and the beep always radiates outward from the point at which it was emitted. So the beep itself doesn't know that Clocky is moving. Clocky is the one doing the moving. So this beep from second 1 will move radially outward, growing in time. A second later, beep 1 has moved. The red dot shows the center of beep 1. Meanwhile, Clocky has moved toward me to the left, and you see that beep 2 has now started, and beep 2 will radiate outward from this point where Clocky is. A second later, beep 1 has continued outward from its starting point, beep 2 has continued outward from its starting point, and now beep 3 has started, and again beep 3 will be centered on where Clocky is at 3 seconds. And again we get beep 4, same thing happens. And what you notice is going on is that as Clocky moves toward me, the beeps are getting bunched up on the direction coming toward me. And so once the beeps reach me, I will hear them coming at me faster than 1 beep a second. I may hear 2 beeps a second. For the last case, let's assume that Clocky is going to move away from me. So beep 1, 2, 3, 4, and now you see that as Clocky moves away from me, the beeps stay centered on the point where they were when they were emitted, and now the beeps are getting further apart, they're getting stretched, and so I will hear the beeping less than once a second, perhaps only every second and a half, or even longer between them. This bunching or spreading of the waves is the Doppler effect. If there's no motion between the clock and me, then the wavelengths stay the same and there is no effect. Now this doesn't mean that we aren't necessarily moving. I mean, perhaps I'm sleeping in a car and Clocky is on the seat next to me, but as long as I am not moving relative to Clocky, I will not experience any Doppler effect. Now, if there is motion, then we will hear a Doppler effect. Motion toward an observer results in the beeps bunching together. And if we're talking about waves, if they are bunched closer together, this means that the wavelengths are shorter, which means that the frequency is higher. And if there is motion away, the waves are spread apart, so the wavelengths are longer, which means the frequency is lower. The faster the relative speed between the two objects, the greater the Doppler effect will be. So in this case, you see that Clocky is moving even faster than in the previous picture, and so the bunching of the waves in the direction that Clocky is moving toward the right is much greater than before, and the spreading of the waves for the observer on the left is much greater than before. So if we can measure how much the waves have changed relative to the way that they started, we can tell how fast an object is moving relative to us. So the Doppler shift also works on light. Let's assume that we have an object giving an emission spectrum. On the top, we see that object as it would appear in a laboratory. In other words, it's not moving. And we see 3 wavelengths of light coming out of this particular object. We see red, we see green, we see blue. Now imagine the object is moving away from us. The wavelengths get longer, and for light, longer wavelengths mean redder colors. And you can see that instead of a bright blue, we have kind of an aqua. Instead of a green, we have a greenish yellow, and instead of a bright red, we have a slightly darker red. That's motion away. And if it's moving even faster, as in object 2, then that shift toward the red, which we call a red shift, that red shift is even greater. Conversely, if something is moving toward us, then the waves get bunched closer together, which means shorter wavelengths, and for light that means bluer colors. And in objects 3 and 4 you see that exact thing. What was a blue line in the spectrum becomes indigo and then violet. What was green becomes kind of aqua and then blue, and what was red becomes ever more orange. We would call this a blue shift. So a blue shift doesn't necessarily mean that the object is becoming blue. You see that the red line only becomes orange. A blue shift just means that the lines have moved to shorter wavelengths. And if we compare the stationary object with object 4 that's moving toward us, you notice that the blue line in the stationary object becomes purple. We would still call that a blue shift because the wavelength has become shorter, even though the color was blue and no longer is. So if the wavelength gets shorter, that is called a blue shift, that is motion toward us. If the wavelength gets longer, that is called a red shift, and that is motion away from us. One point about the Doppler shift is that it only tells us about the part of an object's motion toward or away from us. So here we see me looking at 3 stars. All 3 stars are moving in the same direction at the same speed. However, the top star is moving straight at me. The middle star is moving kind of sideways relative to me, and the bottom star is moving almost directly sideways relative to me. The top star, because it's coming straight at me, I would see the biggest shift. For the middle star, it's only coming part way at me, so I would see a smaller blue shift. And for the bottom star, if you look carefully, you see it's actually moving slightly away from me as well as sideways, so I would see a very slight red shift for that star. So if an object is moving sideways relative to us, if it's moving across our line of sight, not getting any closer or any further away, there will be no Doppler shift. So let's summarize. Takeaway points for this mini lecture. The Doppler effect is the change in wavelength because of relative motion between the source and the observer. And it doesn't matter which one's moving and which one's standing still. As long as the two are getting closer together, there will be a blue shift. As long as they are getting further apart, there will be a red shift. If the two objects are getting closer, the waves are bunched together, which means we have shorter wavelengths and a higher frequency, which means bluer light or a blue shift. If the two objects are getting further apart, the waves get stretched, which results in longer wavelengths, which means lower frequencies, which we call a redshift. And if an object is moving across the line of sight, then there is no Doppler shift. So now we have completed this mini lecture. You may now go on and try the response to this mini lecture.